This video looks at the impact of changing the input weighting on predictive control. Previous videos then have demonstrated through examples and argument that if you have a large output horizon and an input horizon typically of at least 3 but often greater, then the optimization you get from GPC is usually well posed. You'll get sensible predictions and probably sensible performance. However, so far the examples have not considered the impact of the weighting on the input upon the optimization. Now, for multivariable systems, there are in fact other weights, because you can differentially weight different inputs and different outputs and so on. However, in my view, I'm a little bit skeptical about how systematic you can be with regards to the choice of these weights unless you start from some form of economic function, and therefore I'm not going to go into that in any detail. However, for CISO systems, you can reduce the performance index to having a single weight, basically the differential weighting between the inputs and the output errors, and that does allow you to get some relatively simple insight and thus a sort of pseudo systematic design. I'm not going to pretend that it's really systematic. What this video is going to do then is overlay the plots with several different choices of the weights in order to try and gain some insight into what happens as you change the weights. Typical performance index then looks like this. You'll see we have the predicted tracking error squared, and we have a weight, lambda, times the predicted changes in control. Now, as you can see in the CISO case, there's a single weight, that's this lambda term, which expresses the relative importance of actuator movement as compared to tracking errors. And the principle is quite simple. If you make lambda larger, then what it's saying is I don't want the control to change. I want the control increments to be small, and logic for doing that could be less actuator fatigue, and the consequence is that you may have larger tracking errors. So if you increase lambda, you expect the input to move more slowly, but the tracking errors may be larger. However, there may be some other impacts, as you will see as we go through the examples. Now, this video is going to use many times things like ny equals 15 and u equals 4 as typical values that are often large enough, but we will vary that when we need to, and we're going to explore the impact of changing lambda in the performance index. What you will see is what constitutes a long enough prediction horizon, or indeed a long enough control horizon, is not fixed by the example. It can be varying, and that is perhaps confusing in the long term, so we need some ways of dealing with it. Now, just a reminder that we're going to assume that the feed forward is constant for these videos and deal with that issue later. Here's example 1 then, and you'll see what we've done is given the plots for a number of different lambda. Now, unsurprisingly, what you can see is that as lambda gets larger, and therefore implicitly the control actions get smaller, then the responses slow down. But here's the more interesting point. Up to a lambda of about 10, you can make an argument that these predictions within the horizon are pretty good, and the steady state error beyond the horizon is pretty good, and you say, yep, I'd be happy with those. But when you use lambda equals 100, you now have a prediction which is not very good, because the prediction beyond the horizon has quite a large offset, and therefore if you were using lambda equals 100, then ny equals 15 would not be long enough. If I increase ny to 50, you might say, look, I just need a longer horizon, let's take ny to 50 and see what happens. But interestingly, with lambda equals 100, you can still see quite a sizable offset. And so there's an interesting point here. As I increase lambda, the required output horizon seems to be increasing quite significantly, and perhaps disproportionately to what I'm doing with the lambda. And the reason for this is obviously that the inputs have been forced to slow down. So if I look at the corresponding input signals, you can see with small lambda over here, I've got quite aggressive inputs, they jump up and down. But when I've got a large lambda, you can see the input changes very slowly indeed, and it's still changing along here, but you can't see it particularly well. And the problem is that because you've only allowed yourself 4 moves, and because you've penalized the size of the input, it said, well, these have got to be small, and it's not really able to deliver what you want. So a high input weighting implies small increments in the control, and therefore, and here's the key thing, we might need far more than 4 control moves to get to the steady state that we want. Here's an example then, the same example, but what I've done is, you see, I've made NU equal to 15, so I've given myself lots and lots of control moves to try and deal with this issue. And what do you notice? Now, NY of 25 is more than ample. So the biggest problem wasn't really that the output horizon wasn't long enough, the problem was that the input horizon wasn't long enough, because I didn't allow myself enough time for the inputs to get to the steady state. But if I go to n equals 15, now I've got time, and now I can actually get quite good behaviour with lambda equals 100. And if you look at the input signals with NU equals 15, you can see here that the input is changing gradually. It's taking quite a while to get to the steady state, and that's why we needed the NU to be quite large in order to deal with this lambda equals 100. But if lambda was much smaller, then you could have got away with a much smaller input horizon. What about example 2? Well, in this example, the predictions are pretty lousy. If I use ny equals 15, you can see that beyond the horizon, the predictions are not really anything like what I want them to be. So we can straight away say ny equals 15 isn't going to do a good job for us here. And that's because this open loop system has quite a slow mode in it. If lambda is large, then the issue is just exaggerated, it's made worse. What if I try a larger ny then? So now I've gone to an ny of 30, and now you can see that that horizon is just about long enough in order to capture the key dynamics of the outputs, and for the smaller values of lambda, it's just about good enough. You might even argue for lambda equals 100, it's just about good enough in this case, but you're still getting some offsets over here. Now again, there is an issue here likely to be restricted to the fact you've only allowed yourself 4 control moves, and it's difficult to optimize predictive performance and reach steady state while at the same time saying my control moves need to be small, which is what these lambdas are going to do. So what if we try NU equals 10, which allows us more control moves and smaller increments in order to get to the steady state? And what do you notice? You've got much better behavior in general. Okay, you might argue that with lambda equals 100, NU equals 10 is not quite enough, but with these other lambdas, NU equals 10 is just about done the job that we need. Now, what you'll see is with the highest weighting, lambda equals 100, actually, I need to take NU up to nearly 20. Here, I've taken NU to be 18, you can see, and now I've got output predictions with negligible offset. So with lambda equals 100, with this example, I need an NU of nearly 20 in order for the predictions to behave sensibly within my prediction horizon and sensibly beyond the prediction horizon. And if you look at the inputs, it's not going to surprise you to see that with lambda equals 100, the inputs are still changing around here. And so in order to access the input trajectory, which corresponds to the performance index you're using, you have to give it 15, 16, 17, 18 control moves. Otherwise you cannot access this input trajectory, which is the input trajectory that you want. What about example 3? Example 3 was this unstable systems, and in this particular case large values of weighting can actually be problematic, and the reason for that is if you have an unstable system you need a high gain controller. And a high gain controller means you must allow the inputs to be active and aggressive. If the purpose of increasing lambda is to reduce the input activity, then it's likely to be counterproductive when it comes to controlling an unstable system. And that's what you can see here, that as you increase the weighting, the behavior gets worse, even though NU is 4, which should be big enough. In this particular case then, changes to NU and NY are not likely to change much of the insight, as the dominating issue here is the fact we've got an open loop, unstable process. What about example 4? Now here I've taken ny equals 15, nu equals 4, and you can see that with low values of weighting, some of these examples up here, we're not too bad. It's doing a reasonable job. But again, as you increase the lambda and slow down the input activity, what do you find? Your predictions are getting worse and worse and worse. And so clearly, an output horizon of 15 is not good enough in this case, and you might also be making an argument an input horizon of 4 is not good enough. So the horizons need to be large enough to capture the expected performance, and this is key. You've chosen a performance index which weights the errors and the control increments, and that will indicate the sort of performance you expect. And if lambda is very large, then that performance could be quite slow. So, in this case, you'll find we need to take NU up to about 25, which is a very large NU. So this is what we get with NY equals 40, NU equals 25, and lo and behold, you look at the output predictions, and now they move reasonably smoothly, given there's an oscillatory mode. They get to the steady state within the horizon, they stay at the steady state beyond. But you needed to use a control horizon of around 25, and you look at the control moves here, and what do you notice? The optimal control trajectory is changing over about 25 samples, so you cannot access that in your predictions unless NU is as big as 25. So some reflections. To get a well-posed optimization, both the input and the output horizon have to be large enough. Now, the output horizon must include enough of the steady-state errors so that the long-term predictions match what is really wanted. And the obvious test for this is when you do an optimized prediction, do the predictions actually go to the steady state within the horizon and stay at the steady state beyond? What about the input horizon? Well, you have to have enough terms so the control increments can do several things. They need to be able to get the system to steady state. They need to have enough flexibility to counter any undesirable dynamics in the open loop. They need enough flexibility to actually optimize performance during transients. And of course, in addition to that, there needs to be enough steps so they can get to the steady state while managing the input activity, and that's probably here. So the output horizon must be many more samples than it takes for the predictions to get to steady state, and usually this means well beyond the open loop settling time. You'll see in a couple of videos time we clarify exactly what we mean by that. The input horizon needs to be long enough, and this is the key thing, to capture the ideal closed loop input trajectory. So you have to have in your head an idea, what is the ideal closed loop input trajectory, and NU needs to be long enough so you can capture that, because if it's not within your prediction class, your optimization will not be able to find it. Now, if you're using large values of lambda, this could be close to the open loop settling time, or even longer, in fact. In practice, and this is a bit of a note, you may find that smaller values of NU often give you a similar first choice for U, and so your control loop gives you similar behavior with a larger NU and a smaller NU. But my particular point is that you're getting this by accident, not by design, and therefore there could be unseen dangers in using a low NU. Some conclusions then. The horizons NY and NU, and this is the key thing, they are not tuning parameters. And from my view, they are not options, because if you don't choose them right, then it means your optimization is ill-posed. So that optimizing J need not imply sensible or good overall trajectories. Optimizing J tells you the best you can do with restricted degrees of freedom over a restricted horizon, and that's really important. So it's not necessarily optimal at all, because you've arbitrarily restricted your degrees of freedom and restricted your horizon, and therefore it could be seriously flawed, this optimization, if those restrictions are not wisely chosen. So you can have confidence with GPC or DMC type of algorithms if and only if, that's the key point, if and only if the horizons are long enough. and it may take some offline testing to actually establish what is long enough. And you've seen here that in some examples, long enough might mean that NU has to be 20 or so and NY has to be 30 or 40. The required horizons as well may change, and this is important. They may change with the control weighting. So you can't say, here's my system, and therefore the required horizons are X or Y, because when you change the control weighting, the required horizons may change. And so my recommendation, and we'll cover this in a couple of videos' time, is you start from your expected ideal closed-loop responses, and that will give you an idea of the sort of horizons that you need. Now, some caveats. Viewers may note many examples where GPC appears to give very poorly defined predictions, and yet the closed-loop implementation gives reasonable behavior. And that's something that was observed in the early literature. Often GPC worked quite well, but people never really noticed that the predictions weren't that wise. So in essence, what happened was the use of feedback, that is updating every sample, can sometimes save an otherwise ill-thought-through strategy. Now, my view is that even though these examples work, this is by accident, not by design, and therefore you should exercise extreme caution. And the key point to finish with is, why do predictive control poorly when you can do it well? Why choose the horizons to be poor choices when you can actually be systematic and make good choices?